Hello and welcome back to the course on deep learning. In today's tutorial, we're talking about gradient descent. What we learned previously was that in order for a neural network to learn, what needs to happen is backpropagation. And that is when the error, the difference or the sum of squared differences between y hat and y is backpropagated through the neural network and the weights are adjusted accordingly. So we saw that, and today we're going to learn exactly how these weights are adjusted. So let's have a look. This is our very simple version of a neural network, a perceptron or a single layer feed-forward neural network. And what we can see here is this whole process in action where we've got some input value, then we've got a weight, then a activation function is applied, we get y hat, and then we compare it to the actual value, we calculate the cost function. So how can we minimize the cost function? What can we do about it? Well, one approach to do it is a brute force approach, where we just take lots of different possible weights and look at them and see which one works best. And what we would do is, for instance, we'd try out, for let's say, for example, 1,000 weights, and we'd try them out. We'd get something like this for the cost function, and this is a chart of on the y-axis you have cost function, on the vertical axis, on the horizontal axis you have y hat, and because you can see the formula is y hat minus y squared, this is what the cost function would look, something like that. And basically you'd find the best one is over here. So very simple, very intuitive approach. Why not do this brute force method? Why not just try out 1,000 different parameters or inputs for weights and see which one works the best? You'll find the best one that way. Well, if you have just one weight to optimize, this might work. But as you increase the number of weights, increase the number of synapses in your network, you have to face the curse of dimensionality. And so what is the curse of dimensionality? The best way to describe this or explain it is to just look at a practical example. So remember this example we had when we were talking about how neural networks actually work, where we were building or running a neural network for property evaluation. So this is what it looked like when it was trained up already. Well, when it's not trained, before it's trained, before we know what are the weights, the actual neural network looks like this, right? Because we have all these different possible synapses, and we still have to train up the weights. And here we have a total of 25 weights. So 4 times 5 at the start, plus 5 more from the hidden layer to the output layer, 25 weights total. And let's see how we could possibly brute force 25 weights. It's a very simple neural network right here. Very simple, just one hidden layer. And how could we brute force our way through a neural network of this size? Well, let's do some simple mathematical calculations. We have 25 weights, so that means if we have 1,000 combinations that we're going to test out for every weight, the total number of combinations is 1,000 to the power of 25 or 1,000 or 10 to the power of 75 different combinations. Now let's see how Sunway Taihu Lite, the world's fastest supercomputer as of June 2016, how would it approach this problem, right? So Sunway Taihu Lite, it looks like this. It's a whole huge building pretty much for this one supercomputer, and it got the Guinness World Record for being the fastest supercomputer. Right now, it is the fastest supercomputer in the world, and Sunway Taihu Lite can operate at a speed of 93 petaflops. Flop stands for floating operation per second. So it can do 93 to the power times 10 to the power of 15 floating operations per second. That's how quick it is. In comparison, average computers right now, they do like just over several gigaflops and so on. So like kind of those ranges, way less than Sunway Taihu Lite. So Sunway Taihu Lite is in the forefront of technology. And let's say hypothetically that it can do test one combination for our neural network in one flop, basically in one floating operation. That is not possible. That is not practical because you need multiple floating operations to test out a single weight in your neural network. But even let's give it a head start. Let's say that it can do that in a ideal world. It can do that in one floating operation. It can do one test per one floating operation. That means it will still require 10 to the power of 75 divided by 93 times 10 to the power of 15 seconds to run all of those tests, to brute force through that network. So that means approximately 10 to the power of 58 seconds. And that is the same as 10 to the power of 50 years. That is a huge number. That is longer than the universe has existed. And that is definitely not going to, this number is so huge, it's just definitely not going to work for us at all in our optimization. So there we go. This is a no-no even on the world's fastest supercomputer, Sunway Taiyu Lite. So we have to come up with a different approach. How are we going to find the optimal weight? By the way, our neural network was very simple. What about if the neural network looks like something like this, right? Or even greater than that? Then, yeah, it's just not going to happen at all, ever. So the method we're going to be looking at is called gradient descent, and you may have heard of it already. If not, we will find out what it is right now. So there's our cost function, and now we're going to see how we can come up with a faster way to find the best option. So let's say we start somewhere. You got to start somewhere. So we start over there, and from that point in the top left, what we're going to do is we're going to look at the angle of our cost function at that point. So we're just going to basically, that's why it's called gradient, because you have to differentiate. We're not going to look at the mathematical equations. We will provide some tips on additional reading at the end of the next lecture. But basically, you just need to differentiate, find out what the slope is in that specific point, and find out if the slope is positive or negative. If the slope is negative, like in this case, means that you're going downhill. So to the right is downhill, to the left is uphill. And from there, it means you need to go right. Basically, you need to go downhill. And that's what we're going to do. Vroom. Takes a step, right? The ball rolls down. Again, same thing. You calculate the slope. This time the slope is positive, meaning right is uphill, left is downhill, and you need to go left. And you roll the ball down. And again, you calculate the slope and you roll the ball right. There we go. So that's how you find, in simple terms, that's how you find the best weights, the best situation that minimizes your cost function. Of course, it's not going to be like a ball rolling. Is going to be a very zigzaggy type of approach, but it's easier to remember, or kind of it's more fun to look at it as a ball rolling, but in reality, yes, you just it is going to be like a step-by-step approach, so it's going to be a zigzaggy type of method. Yeah, and also there's lots of other elements to it. There's things like, for instance, why does it go down? Why does it not like go away over the line? So it could have jumped out of this, gone upwards instead of downwards, and things like that. So there are parameters that you can tweak, and again, we will mention where you can find out more on that, and plus we'll have this in the practical application. But in the simplest intuitive approach, this is what is happening. We are getting to the bottom by just understanding which way we need to go. Instead of brute forcing through thousands and thousands and millions and billions and quadrillions of combinations, we can just simply every time have a look at which way is it sloping. So right, like you imagine you're standing on a hill, which way does it feel that it's going downwards? And whichever way it is going downwards, you just keep walking that way. You take 50 steps that way, and then you assess again. Okay, which way is it going downwards? This way. Okay, now take 50 steps or less, take 40 steps that way. So it gets less and less and less as you get closer. So here's an example of gradient descent applied in a two-dimensional space. So that was a one-dimensional example. Here we have a two-dimensional space for the gradient descent. As you can see, it's getting closer to the minimum. And it's also called gradient descent because you're descending into the minimum of the cost function. And finally, here's the gradient descent applied in 3 dimensions. This is what it looks like if you project it onto 2 dimensions. You can see it's zigzagging its way into the minimum. So there we go. That was gradient descent. In the next tutorial, we'll talk about stochastic gradient descent. It'll be a continuation of this tutorial, and I look forward to seeing you there. Until next time, enjoy deep learning. Hello and welcome back to the course on deep learning. Today we're talking about stochastic gradient descent. Previously, we learned about gradient descent, and we found out that it is a very efficient method to solve our optimization problem where we're trying to minimize the cost function. It basically takes us from 10 to the power of 57 years to solving a problem within minutes or hours or within a day or so. And it really helps speed things up because we can see which way is downhill and we can just go in that direction and take steps and get to the minimum faster. But the thing with gradient descent is that this method requires for the cost function to be convex. And as you can see here, we've specifically chosen a convex cost function. Basically, convex means that the function looks similar to what we're seeing now, that it's just convexed into one direction, and that it in essence has one global minimum, and that's the one that we're going to find. But what if our function is not convex? What if our cost function is not convex? What if it looks something like this? Well, first of all, how could that happen? Well, that could happen because if we first of all choose a cost function which is not the square difference between y hat and y, or if we do choose the cost function which is like that, but then in a multidimensional space it can actually turn into something that is not convex. And so what would happen in this case if we just try to apply our normal gradient descent method? Something like this could happen. We could find a local minimum of the cost function rather than the global one. So this one was the best one and we found the wrong one, and therefore we don't have the correct weights. We don't have an optimized neural network. We have a subpar neural network. And so what do we do in this case? Well, the answer here is stochastic gradient descent. And it turns out the stochastic gradient descent doesn't require for the cost function to be convex. So let's have a look at the two differences between the normal gradient descent that we talked about and the stochastic gradient descent. So normal gradient descent is when we take all of our rows, we plug them into our neural network. And once again, here we've got the neural network copied over several times, but the rows are being plugged into that same neural network every time. So there's only one neural network. This is just for visualization purposes. And then once we've plugged them in, we've calculated our cost function based on the formula on the right and looking at the chart at the bottom. And then we adjust the weights then. And this is called the gradient descent method, or it's also the proper term is the batch gradient descent method. So we take the whole batch of from our sample, we apply it, and then we run that. The stochastic gradient descent method is a bit different. Here we take the rows one by one. So we take this row, we run our neural network, and then we adjust the weights. Then we move on to the second row. We take the second row, we run our neural network, we look at the cost function, and then we adjust the weights again. And then we take another row, take row 3, we run our neural network, we look at the cost function, we adjust the weights. So basically, we're looking at we're adjusting the weights after every single row rather than doing everything together and then adjusting weights. Two different approaches, and now we're going to just compare the two side by side. So here they are. This is how to visually remember them. So you've got the batch gradient descent where you're adjusting the weights after you've run all of the rows in your neural network. And then basically you adjust the weights and you run the whole thing again, iteration, iteration, iteration. In the stochastic gradient descent method, you run one row at a time and you adjust the weights, you adjust the weights, you adjust the weights, and then you do everything again and again. And that is called the stochastic gradient descent method. The main two differences are that the stochastic gradient descent method helps you avoid the problem where you find those local extremums or local minimums rather than the overall global minimum. And the reason for that in simple terms is that the SGD, or the stochastic gradient descent method, has much higher fluctuations because it can afford them. It's doing one iteration or one row at a time, and therefore the fluctuations are much higher, and it is much more likely to find the global minimum rather than just the local minimum. And the other thing about the stochastic gradient descent method compared to the batch gradient is it's faster. Like the first impression that you might have is because it's doing every single row one at a time, it's slower, but actually, in fact, it is faster because it doesn't have to load up all the data into memory and run and wait until all of those rows are run all together. It can just run them one by one, so it's a much lighter algorithm. It's much faster in that sense. So though it has way more, in those senses, it has more advantages over the batch gradient descent method. The main advantage of, or the main kind of like pro for the batch gradient descent method is that it is a deterministic algorithm rather than stochastic gradient descent being a stochastic algorithm, meaning it's random. And with the batch gradient descent method, as long as you have the same starting weights for your neural network, every time you run the batch gradient descent method, you will get the same iterations, the same results for your for the way your weights are being updated. For the stochastic gradient descent method, you won't get that because it is a stochastic method. You're picking your rows possibly at random, and you are updating your neural network in a stochastic manner, and therefore you're just going to, every single time you run the stochastic gradient descent method, even if you have the same weights at the start, you're going to have a different process, different iterations to get there. So that's in a nutshell what stochastic gradient descent is. Also, there's a method in between the two called the mini batch gradient descent method, where you combine the two and you basically run, rather than running a whole batch or running one at a time, you run batches of rows, maybe 5, 10, 100, however many rows you decide to set. You run that number of rows at a time, then you update your weights, and so on. And that's called the mini batch gradient descent method. If you'd like to learn more about gradient descent, there's a great article which you can have a look at. It's called A Neural Network in 13 Lines of Python, Part 2, Gradient Descent by Andrew Trask. And the link is below. It's on GitHub, 2015 article. Very well written, in very simple terms. It's got some interesting philosophical or just interesting thoughts on how to apply gradient descent, what are the advantages and disadvantages, and how to do things in certain situations. So it's got some very cool tips, tricks, and hacks. Very easy read, so definitely check that out. And another one, a bit more heavier read for those of you who are into mathematics, who want to get to the bottom of the mathematics, why gradient descent in that specific, what are the formulas that are driving gradient descent, how is it calculated, and so on. Check out the article, or actually the book. It's a free online book called Neural Networks and Deep Learning by Michael Nielsen, 2015 book. It's just basically, it's all online. You can go ahead and check it out there. And they're, again, very soft introduction to the mathematics, but the mathematics are pretty heavy as you go along, as you read through the article. But at the same time, it gets you into that mood. I think even it has like a warm-up chapter where you first warm up with the math and then you jump into them. So interested in math, then this is the article to go to. And there we go. So that's in a nutshell the difference between gradient descent and stochastic gradient descent, and how the two work. And on that note, we're going to wrap up today's tutorial. I look forward to seeing you on the next one. And until then, enjoy deep learning.